might check the attendance today, so don't leave early. I mean, if you care about the 1 3 point. So the midterm exam is done. The grading is done. I'm supposed to get it this afternoon. I got the Excel file that summarizes your performance, and it turns out to be extremely well. Class average was around like 83, and 8 people out of 42 got 100 out of 100, which is aced. So it's a pretty good performance. Should feel okay about it, and feel great about it too. In order to make things fair, the final is going to be a little bit more challenging, like I said. Some of those questions that I initially put on the exam, but I just deleted them in the last second. One of the questions on the Bayesian stuff was replaced by a simple question about the conditional probability. So that in some sense helped you guys perform better than I expected before the exam. But all in all, it was a nice performance. So grading is completed, and I'll check it for the last time this afternoon and bring them here tomorrow, and you'll get it back. And make sure that where you went wrong, if there was any problem. Model solutions are posted on the class website this morning. If you go to the class website, you'll see this file. Midterm exam solutions, 8 pages long. The majority of these questions were used either by the problem set or during the review, so I'm not going to go through these solutions. The only question that you might find a bit challenging would be this last one under part 1, which is about this proving, given this disjoint property between these A and B. You're supposed to prove this simple statement involving probability of A and B, but other than that, should be pretty easy. Yeah. So the one that I talking about was this one. This one was initially about one pretty tough question on the Bayes theorem, but I replaced it. So this is not about Bayes theorem, just simply something about the conditional probability. Almost everyone got this one. And the other 2 questions about the Bayes theorem is rather straightforward. And the third one is almost the same as one of the big questions we tried during review, which was about the probability mass function for discrete random variables. So you must have found them rather familiar and surprising in any sense. So go there, download it, and make sure that you have access to these and compare them. One more thing before we start on the continuous random variable stuff, make a class. We missed 2 lectures, one just before the midterm exam and another one last week before the holiday, the Children's Day. So the 3 candidates, I'm thinking of either 21st, 22nd, or 28th. Any one of these 3 dates, pretty much like after 4, we're gonna use it for the review, not review, make a class. So you think about it, and then we just simply do the class vote, which one is the most convenient one. So in terms of schedules. So think about this, 3 possibilities, and then sometime next week we'll ask you around and then see when is the best fit for your schedule for the make a class. Typically 2 hours long. Between 4 and 6, most likely. So it's Thursday, Friday next week, or Thursday, 2 weeks from now. So any one of these 3. Most likely this classroom, but I have to make sure whether there's no other classes at that time. So that's the possible time for the maker class. Any other thing that you might want to ask for, since it's been quite a long time, 3 weeks? Nothing else? Okay. Let's get started. Which is chapter 8. Not chapter 8, the note 8. The known continuous random variable. So given the definition of the probability density function and cumulative distribution function for continuous random variables, this one plays a major role in continuous random variable case. So why do we call this distribution uniform? Because the density function is fixed at a certain number. So you first specify the support of the density. The value that this PDF function takes on is a non-negative number because it's a probability. But then there must be a certain range over which this the corresponding number for under this function is non-negative, something like 1. But then what's specific, unique about this distribution is that this number is not a variable, it's something fixed. So in this case, it fixed at 1. And then that's the case when this random variable x takes on any real number between 0 and 1. Outside this range, everything basically decays down to 0. No probability for any other choices for x outside this range of between 0 and 1. So if that happens, and if this is a valid way to specify certain distribution, we call that as a uniform random variable. The value taken by this x is something bigger than or equal to 0. But then why in this case the density function must assume the value 1? So what I'm asking is first specify the range. And the range in this case is between 0 and 1. And over this range, this density function takes on some specific number, not negative, but this is constant because it has to be uniform. But what value for this one should be? In this case, that's 1 because how do you know that that's 1? Why not 3 or why not 5? Well, because it's a PDF. For any valid PDF, if you integrate it over the support, in this case between 0 and 1, this one must add up to or integrate to 1. But we don't know that under this uniform distribution case, this f of x is some positive number, some fixed number. So you can replace it by, say, c. And you can solve it backward. So bring this c outside, and then if you integrate it, what you will get is just a 1. So c has to be 1 in this case. So that's not arbitrary at all. So actually can be easily pinned down by solving out this the PDF function. Okay. So this condition, if you integrate this the PDF function over its support, it must integrate 1. Otherwise, it's not a valid PDF. So that's the way to figure out this height of this rectangle, probably the density function, something fixed, but may not be given. If it's a given, you just use it. But if this one's not given, you first have to compute it, just like using ways like this one. But then all you need to figure out what's the corresponding probability density function for this support, and that's simply 1 over alpha, a beta minus alpha. The reason why it's 1 over beta minus alpha, same as this one. The only difference is you generalize it a little bit. So call that as like alpha, and then the upper bound should be beta. Again, the density function should be fixed, some constant number between this support. Say that it's called C. And what's remaining inside just a 1. But then if you integrate the 1 in terms of x between alpha and beta, that's just simply x running from alpha to beta. So that's a beta minus alpha. So c times beta minus alpha. But the whole thing must integrate to 1. So if you solve this equation in terms of c, you'll get 1 over alpha a beta minus alpha. That's fine. If you want to bypass this integral, just go to the picture. Simply the integral of this function under the function between alpha and beta, so it's nothing but the area under this curve. So think about this rectangle. So integral over here is nothing but the area of this shady rectangle. But then any area of a rectangle is the product of the length of base and the height. And length of base is obviously beta minus alpha. So length of this base, simply beta minus alpha. The height is going to be your PDF, which is C. But then the area must be 1 because of this property. And then area for any rectangle is simply the product of this height and the length of the base. So C times beta minus alpha is easily known to be 1. You can solve for C using this condition instead of this. But either way, you still get the same answer. 1 over beta minus alpha. So that's the PDF function for this uniform distribution between alpha and beta. It's a rather straightforward one, but once in a while, students make mistakes in computing this, so you hopefully won't do it when you ever encounter questions like this on the final. So name that as like a big F. Uppercase F is a usual notation for the CDF of this random variable. By definition, supposed to solve out this integral, x running from negative infinity, which is the lowest possible value for x, and running up to this argument, which is a. And then you put the PDF inside. But then the PDF is just some fixed number, which is what we figured out in here. So you just bring this one to in here, and then bring the whole fraction outside, and then solve it out depending on where this a belongs to. So if it's a is strictly less than or equal to alpha, there's no probability mass at all. So the whole probability should be 0. If it's something between alpha and beta, which is of our primary interest, and that's again nothing but the area of this rectangle. So what's happening is this argument, the value taken by this x changes this time, although the support stays exactly the same. So you can divide it into 3 different cases. When this argument x, right there, and I'm supposed to compute the probability all the way up to this x, but there's nothing. So the integral is obviously 0. That refers to this first case. So that's why we get 0, because there's no probability mass to the left-hand side of this alpha. Second case, when alpha, x is bounded by alpha and beta, this area, somewhere in here, bigger than alpha but still less than beta. But then the cumulative probability is nothing but the area of this rectangle. Right? It's either x is equal to this specific point or less. So if you want to compute all the probability under which this curve is defined, it's nothing but the area of this part. But then again, it's simply the product of the base, and base now is this, which is x minus alpha, in this case a. So we put that as a minus alpha here. But then the length of height, that's 1 over beta minus alpha, as we figured out from the previous page. So the product of these two is simply this ratio, and that is going to be the area of this rectangle, shaded in pink. And then the last case is, of course, when this x is bigger than beta, which is the upper bound of this support. So if x belongs somewhere out there, and if you accumulate everything all the way up to x, that's everything. So that's 1. So that's why the last one, the CDF value for this x, if x take on some value bigger than beta, I should integrate to 1. So divided into 3 different cases. When the argument of the CDF is strictly less than the lower bound, there's no probability mass error, so the integral should be 0. Interesting case in the middle one, so bigger than alpha but lower than this upper bound, but then you're supposed to compute the area for this part of the rectangle under this PDF of a random variable x, and the remaining case include everything. So naturally that integrate up to 1 quite easily can be figured out. So it defined it by introducing this PDF function to check its validity by making sure that this condition holds. And then we went on to generalize it to the general case when x is bounded by alpha and beta, could be any real numbers, and generalize the PDF function accordingly. And we figured out the corresponding CDF function as well. Uniform distribution. First example. So given this general uniform distribution between alpha and beta, you are supposed to figure out the expected value of it and the variance of it. And first, the expected value. What should be the expected value of x if x is a uniform between alpha and beta? How do you compute the expected value for any continuous random variable? So go back to the definition. For continuous random variable x, expected value of this x defined to be nothing but an integral. Negative infinity to the positive infinity. And x is a uniform in this case, so the PDF is known. So this function is known, which is this one here. Right? And you're supposed to figure out what's the value for this integral. What is it? The answer is not on the face. So if you go ahead and compute this one, you get something like this. So replace this f of x by its the given density function, which is 1 over beta minus alpha, because it's simply uniform between alpha and beta. So this condition gives us this PDF function, and x is just there because it's from the definition of expected value of x. Simply pull out this fraction, coefficient 1 over beta minus alpha outside, integrate x in terms of x, which is half times x squared, then plug in first beta and then subtract that under alpha, and if you summarize it, you're going to get this one. Alpha plus beta divided by 2. So go back to the picture of this density function. So density for this x in this case between alpha and beta, so raised up to certain height, and then height was 1 over beta minus alpha. So if the mean of this x, expectation of x, turns out to be sum of alpha and beta over 2, where does that point stand? So the point alpha plus beta over 2 is right in the middle of this range. That's the arithmetic mean, which is intuitive because the distribution is evenly spread out. So if you go for the center of this distribution, it should be the middle point, which is alpha plus beta divided by 2. So if the certain probability distribution is uniformly distributed between alpha and beta, on average, the value that will be taken by x is just right in the middle. All right? So that's the mean. What about the variance? How to get the variance? First compute the second moment, which is expectation of x squared, and then use the useful formula, of course. Not done yet. If the exam score, the average is over 80, there are good things and bad things. good things are obviously students are happy, so I don't get any complaints, so that makes my job easy. But the bad thing is, since everybody is just basically clustered around like a very narrow, thin range of the distribution, from the grader point of view, it's just hard to assign letter grades. Can assign like everyone A plus or A0, but sometimes that's not education and not desirable. So I'll come up with a certain way to give some distribution to this class performance. But as far as the midterm exam is concerned, basically everyone got either A or A plus, with like a very few minor cases below like 80 or something. So when I first taught this one, the midterm score average was just around 70. Last year was something between 75 and 80, and this time is over 85. So something might be like something between 90 and 95. But finally, it's a different matter because you have to deal with the center limit theorem, which is the most difficult topic in this class. So just keep up the good work and don't lose your pace. So that's the mean, and if you go to the computation variance, so you get something like that. First, figure out the second moment, which is expectation of x squared. The only difference is that this one should be x instead of x squared instead of x. The others are the same. So get this the value for the second moment, and then you given the first moment, which is a mean, square it and subtract that from the computed expectation of x squared, and you'll get the final answer of beta minus alpha squared over the 12. So that should be the correct variance, so uniform random variable between alpha and beta. We are a bit ahead of the initial schedule compared to the classes from last year. So when we get into June, we might actually start on some of the material in the linear regression, which is mostly covered by the sequel of this one, which is Introduction to Econometrics, when you come back in the fall. But that's a possibility because we are moving a bit faster than the previous time. What was planned before the class began was the last topic was supposed to be hypothesis testing, but given the fact that we are a bit faster than what we planned before, there's certain it's possible for us to get into that regression stuff before this course is over. But there will be something in June, not this month. Questions or comments so far? No? You guys already started the Spring Festival? When is the Spring Festival this year? Not interested? When is it? This week or next? Next week? Still class. It doesn't matter, we meet at 9 in the morning. We're going to start drinking at 9. So continue, which is this one. So it's even simpler. Now we specify a little bit more and give some numbers to those each endpoint. So x is uniform between 0 and 10 specifically. Then supposed to compute 3 different probabilities. First, x is less than 3. Second, x is bigger than 3. And then third, x is bounded by 3 and 8. This one, you don't need any integral. can easily figure out what's the answer for the first. The probability that x is strictly less than 3 if it's a uniform between 0 and 10. Can be anything between 0 and 10. It's evenly distributed over this range, and you're interested in computing the probability up until 3 here. What are the chances? 0.3. What about the second? 0.4. And then half for the last one. But we can formalize it by first introducing or defining this PDF function and then setting up this integral, specifying the range of this integral, and then conducting the computation. But either way, you should get the still same answer. But the key is that the density function is evenly distributed. So it's equally likely to be any one of these points within the range. That's why we can bypass all this computation involving these integrals. Otherwise, we have to do it. Next example. Oh, this one's interesting. So we have a bus. You're supposed to take bus every morning, and then bus comes to a specific stop at 15-minute interval. First bus comes, and then wait another 15 minutes, and second bus comes, and so forth. Starting from 7 in the morning. So buses are supposed to arrive this stop at 7 first. Then if you miss the first bus, second one comes at 15 minutes later, which is at 7:15. And then third one comes at 7:30 and 7:45 and so forth. So if there's a passenger and he arrives at this bus stop at a certain time, and assume that this distribution is uniform between 7 and 7:30. So the key word in this case is that's uniformly distributed. So we do know the distribution. So if that's the case, question is asking us two questions. First, what's the probability that this guy will have to wait less than 5 minutes to catch the bus? And secondly, more than 10 minutes to get on the bus. Starting with the first one. Expected wait time for getting on the bus is less than 5 minutes. What's the probability? So, picture might help if you don't really understand what's going on. So draw some line. So that's simply time. There's a 7, 7:15, 7:30. You are interested in any time after than this one. So buses are supposed to arrive at this stop at either 7 or 7:15 or 15 minutes later than that, which is going to be 7:30. First event, this guy comes to this bus stop and it has to wait less than 5 minutes. Where should that be on this specific distribution? So it has to be either here, 7:05. Oh no, it's less than 5. So he has to wait. He cannot, get the bus right after he arrives. But the wait time is less than 5. So that's gonna be 7:10 here. So he comes to this bus stop at 7:10. And then waits as much as this. The certain wait time is going to be less than 5. Secondly, if you arrive at this bus stop at 7:25, which is right here, the wait time is going to be this. So what are the chances of this? What's that probability? So either case number 1, which is this, or case number 2. There are no other cases. If you have to get on the bus between 7 and 7:30, so this one's asking first to figure out what is the probability. the second case is kind of the opposite. So that's case number 1, A, and that's B. First arrives at the same time, 7. Next one comes at 15 minutes after. Last one comes at 7:30. Now this time you have to wait more than 10 minutes. So that means you either come at something between 7 and 7:05. So the wait time in this case is going to be something like that. It's hard to draw in this case. It's obviously bigger than 10, longer than 10 minutes. Or you arrive between 7:15 and 7:20. So somewhere here, the wait time is going to be again longer than 10 minutes. Either one of these two. So using the uniform distribution, first specify the probability density function of this one, which is this. First define this x to be the number of minutes past the 7. And that one obviously follows a uniform distribution. And then the support for this kind of uniform distribution is obviously between 0 and 30. Then you can accordingly specify each probability using this idea. So if you figure out each probability correctly, the answer for the first one should be a third. And then interestingly, the answer to the second one should be the same at the same probability of 1/3. So with equal probability, both events are supposed to happen. The key in this case is setting up this x to be the number of minutes past the 7, and then you relate that on to this uniform distribution between 0 and 30. Then you're halfway through basically. Rest of them just simply computing the numbers. So if it waits less than 5 minutes, it's either between 7:10 and 15 or between 25 and 30, which is what these pictures are representing. You figure out the probability for each, which can be easily computed using this fact that this is uniformly distributed. And second case, either between 7 and 7:05, so right there, so you wait longer than 10 minutes, or between the 15 and 20. And similarly, you can use the fact that x is uniform between 0 and 30 and find out this probability of 1/3. Uniform distribution. So we define its PDF function, relate that to CDF, and then try 3 examples. First, expected value and variance of it. Some other computational probabilities, and then the last one is a more practical one. Setting up the x such that that's number of minutes past this 7 a.m. thing, and then you're supposed to get the bus. Specifying these two events, have to wait less than 5 minutes or more than 10 minutes. So relate this one to this given distribution of uniform between 0 and 30, and figure out each relating corresponding probabilities. 3 examples. Our next problem set will be posted either sometime this afternoon or tomorrow. And then the quiz 4 is going to be based upon that. Next one, the most important distribution in this case, normal distribution. You must have heard of it before. Density-wise, that's the definition of PDF for normal distribution. So in normal distribution, the 2 key parameters, value at the center, which is mu, and then degree of variance, which is variance, sigma squared. So if this one assumes these 2 parameters, mu first and then sigma squared, probability density function, or simply PDF of x, is given by this mass expression. So that's a PDF of x. So in the case of uniform, so it couldn't be simpler. So that was the PDF of uniform distribution, right there. If you turn to some other continuous random variable, which is called the normal distribution, PDF gets a lot messier. That's its PDF. And most people don't remember this formula, they just simply know the shape of it. So if it's a normal distribution, some kind of like a bell curve, so in the middle there's a P, the center value, which is named as like a mu, and it takes the variance of sigma squared. And if you materialize this density, attach certain formula to it, and that's going to be this one. That's the PDF of this curve thing. Who first figured out this function? Some French guy. So when you take the exam, and the students often ask questions such as, are you going to curve this class? So the word curve comes from this normal distribution. Because from the fact that this one takes this bell-shaped curve. Complete symmetry around mu with certain degree of spread or variation. So a bit of history about this famous and popular but very powerful normal distribution. First guy who invented this one, so you give me like a 15 minutes, I still don't figure out how to pronounce this name, some French guy. Does anybody know French in here? How do you pronounce this last name? Help me a bit. Anyone? Never mind. Some guy. So back in 1733. So the motivation for this one, this mathematician to come up with so-called normal distribution, because he wanted to approximate binomial distribution. So approximately this one is associated with binomial variable. When the binomial parameter n, which is number of trials, is very big. Sounds familiar? In the discrete case, what was the effective way to approximate binomial distribution? That was Poisson. So when sample size is big, number of trials is big, and the success probability is relatively low, n times p, which is a mean of binomial, is tractable, manageable. In that case, it can be approximated pretty much accurately by Poisson distribution. But Poisson is a discrete random variable. But if you have to approximate the same binomial using this time something continuous, your choice is going to be this normal distribution. And that was the motivation why this French mathematician come up with this distribution called the normal. This normal distribution plays another very important role for different reasons, and that's because of the central limit theorem. For the remaining part of this course, the most important theoretic result is the central limit theorem. For the first step, it was a Bayes theorem. So basically, final exam will be entirely built around this simple idea of central limit theorem. We'll define it and then try numerous different examples when we get to the second half of this month, starting next week, I think, or maybe in 2 weeks. So two reasons why the normal distribution plays a central role in this class. First one, that's the effective way to approximate binomial. When the sample size gets extremely large, the role was in some part played by the Poisson, which was another discrete random variable. But if you introduce the same kind of approximation in the continuous case, that role is going to be done by this normal distribution. And second reason why this is so crucial, because it's a closely related so-called central limit theorem, which we will define and investigate extensively in the second half of this month. So in fact, this CRTA, we simply call that as a CRTA. Take the initials, C there, L there, and T there. CRT is one of the two most important results in probability theory, and the other is so-called the strong law of large number, which we will also cover in the second half of this month. So those are the two central pieces in modern theory and probability. And then since normal distribution is closely related, one of those pillars, very important results in modern probability theory, that one certainly deserves some attention. But there's a bit of historical background. Who invented this one, and what was the motivation, and what's the reason why you have to cover in this course? In part because that's a good way to approximate Poisson binomial, and second reason because it's closely related to so-called central limit theorem. the mean of this the random variable, so-called normal distribution with this PDF, is nothing but this parameter mu. So that's the mean, and variance is this sigma squared. How do you derive this one? It's difficult, so you pass it. First time I was teaching this one, I actually did it, but the students didn't like it because it's so complicated. So given this probability density function, you just know that the mean function is the number in here, mu, and variance of this density function variable is going to be sigma squared. And same sigma appears here too. So the first parameter mu, that's simply the mean of x when x follows normal. And second parameter sigma squared is nothing but the variance of it because of these results. And how do you derive it? There's a way, but difficult, so we don't cover it in this class. What we are going to do, take these facts, accept them, and then use them for some other purposes. One of them is this one. So assume that x follows normal distribution, and mean of this guy is mu, and variance is sigma squared. You might transform this original x into something different, which is a second variable y. Relation between the original x, which is normal, and this newly defined one is given by this linear transformation. First, multiply this original x by some number alpha, and then add another fixed number beta to it, and then you can easily define this second variable y. But then, interestingly, this second variable y is also normal distribution, but there's a slight change in its mean and its variance. You want to figure out why. So the way to figure out the distribution of certain transformed process, you first, like I said many times, first go for its CDF function and then derive its PDF. So start with a CDF of this y, because the PDF and CDF of x are already given to us. So by definition, PDF of this second variable y defined by, it's not given there. I was running out of space, so I just hit that. So define second variable y to be alpha times x plus beta, where alpha is positive. Beta doesn't have to be. Some fixed number. Then the CDF second variable y given by big F, and the argument takes on little a. That's nothing but the probability such that this big Y either equal to or less than this step. And then the second step comes in, because Y is nothing but alpha times x plus beta either equal to less than a. So I skip this one. You can put it back if you want. So start with the CDF of the second process y, which is nothing but this one. But then using the relation between x and y, you can write that as x is either equal to or less than the fraction, which is a minus beta over alpha, using this relationship between x and y. But that's nothing but the CDF of x, right? So the whole probability here, so either equal to or less than a certain number there, but then the argument on the left-hand side is nothing but x. So that's a PDF of x, a CDF of x. So given the CDF of the second process y, your job is to figure out the corresponding PDF this time. And then how do you get the PDF from the given CDF when that random variable is continuous? You simply integrate, differentiate it in terms of the argument, which is a in this case. Which is another well-known fact. Given the CDF, if you differentiate the whole function in terms of this argument, you'll get the PDF of x, which is exactly what we are using down here. So if you integrate the, keep saying integrate. differentiate the left-hand side of the statement, which is uppercase f sub y of a, in terms of a, you simply get the PDF of y on the left-hand side, which is small f sub big Y in terms of small a. If you do the same operation on the right end, which is this one, since this quantity here is exactly the same as this one, first differentiate in terms of a using this first representation, you get this one. And then if you do the same operation on the right end, which is this, first uppercase f becomes the lowercase, but then there's a chain rule involved. You also have to differentiate the stuff inside this big bracket. And that's nothing but 1 over alpha. That's why the 1 over alpha is used as a second coefficient. So the general rule here is a chain rule. And chain rule states, in case you haven't heard it, there's a famous results in basic calculus that, no, not that, just state it. Differentiate the whole function in terms of x, but then function is made up of like two different functions, composite. So that's possible. The first function inside, which is g of x, but then there's the outer function, which is second function f. First integrate the whole function, which is outer function. And then you multiply it by integral, not integral, derivative of this inner function. That's chain rule. So you first term, get on this outer function, which is f, and that's this one. But then there's an inner function inside this bracket, and then you differentiate that. So that's a chain rule. And if you apply this to this composite function, outer function becomes a small f of x, small f sub x. And the inner function there, if you differentiate in terms of a, nothing but 1 over alpha. So it's just direct application of this chain rule there. But then the PDF of x is given, right? PDF of x was given way back in here. So that's the PDF of x. So you can just bring the exact formulation there and put it in here instead of this guy. And the only difference is the argument of this PDF is no longer x, but this fraction, which is a minus beta divided by alpha. Rest of them is the same. So previously this was simply small x, but then there was a slight change in this argument that replaced this small x by the whole stuff inside this bracket, which is this. The other rest of this expression, mu is the same as before, twice sigma squared is the same as before, same exponential function, and then the outer coefficient. Up until this one is exactly the same, but then you have another 1 over alpha thing outside, so you have to multiply that one by 1 over alpha 2. So that is going to be the PDF of y, which is what we are eventually after. You can summarize a little bit further to figure out the mean and variance of the second process y by first expanding the term inside. So since you have to divide the a minus beta by alpha, you can do the same thing for this second one, which is mu. But then you can bring this 1 over alpha thing outside, but then there's a square. So 1 over alpha gets squared, which is 1 over alpha squared. So put that down here, and then inside takes a similar form as before, such that we can easily figure out that's the mean, and that's the variance. So in summary, what's going on is the following. So whole result, so basically telling us nothing but this. X normal with mean, mu, and variance of sigma squared. If you transform this x using some kind of linear transformation, which is alpha times x plus beta, This linear transformation again is normal distribution. So normality is preserved under the linear transformation, but there's a slight change in the mean and variance. Mean is going to be alpha times mu plus beta, and again the variance is going to change, which is alpha squared sigma. That's what the whole derivation is basically telling us. So original x, so normal with mean of mu and variance of sigma squared. As long as the transformation stays linear, which is this one, so there's original x inside. You first times alpha and then plus another number. Normality is preserved. Still it's normal. So normal there, normal down here. And the only difference is there's a slight change in the mean and variance. New mean is going to be simply mu instead of x, which is alpha times mu plus beta. And then variance, addition doesn't matter, you drop it. But then since you have another coefficient alpha, you have to first square it and then multiply that one by the initial variance of it. So that's going to be the new variance. That's such a long way to say it. It's a simple statement. Still have to verify, otherwise you don't know. So on an exam, distribution should be pretty much the same as before. It's just a normal distribution. Underlying distribution of x still be normal. But I can switch this transformation into something different, like a logarithm or exponential. Then you have to figure out what's going to happen to this normality. So what I'm saying is that instead of this, I can say, what's the distribution of log of x? That's one possibility. Or I can say, what's the distribution of exponential of x? Some other transformation. Certainly not linear, but then you still can figure out what's going to be the distribution of this and that using the same kind of methodology that we are using here. So that's one way to extend this problem. And let's see whether you fully understand this whole thing. All right? But things are rather simple in this case because everything is linear. It's certainly a more straightforward case, but it doesn't have to be. So if you extend this result, one very important transformation of this original normal is going to be the following. So literally this alpha and beta can be anything, any fixed number. So one way to put this alpha and beta in this setup could be the following. Right? So it's another linear transformation. So alpha in this case is going to be 1 over sigma, and beta is going to be negative mu over lambda, not lambda, the sigma. So if you rewrite this one, that is nothing but right? It's just the same thing as saying this. But then that's basically your alpha, and that's basically your beta. Right? Because alpha and beta can be any real number. That's a one representation of those real numbers. So what's the mean? What should be the mean of this new process? We had a result. We handled the most general case of alpha and beta. Mean was alpha times initial mean of mu plus the second number, which is beta. And alpha and beta take on these specific values in this case. So what should be the mean for the second process? 0. Yeah. What about the variance? 1. Yeah, exactly. So this one's called the standard normal distribution. which is nothing but some kind of specific kind of linear transformation of the original normal, which is x. Since it's a special case, so mean simply 1, 0, and the standard deviation simply of 1. This one is a special notation which is z, and that's a notation for so-called standard normal random variable. Why standard? Because mean becomes 0 and then standard deviation becomes 1. And notation for this one is specifically z. How do you know that this is still normal distribution? Because of the previous result. We covered the general case and showed that the transformed y still normal. Normality is still preserved. So the same rule should apply to this more specific case. So even if there's a transformation of this original x, the resulting process is still normal distribution, but special kind of normal distribution with a unit mean, zero mean, and then unit variance. So this one is called the standard normal distribution.